So firstly, let's say we have a straight line, right? Straight line. And we know that's given by y is equal to mx plus c, where m is the gradient of the line. We already know this. But what if instead we had a curve that looks something like this? Went down and then went back up, right? Let's say that's a curve that we had. Does this curve have a gradient? Or what does it mean for a curve to have a gradient? Is that a thing? Does it make any sense? Well, the answer is yes and no. So the curve does not have a gradient, but each point on the curve has a different gradient. So let's say we have this curve, right? We'll choose our own example. Let's say we have let me draw that better. Let's say we have y is equal to x squared plus 2x minus 3, right? I can tell you it's going to look something like this. Something like that. And to get the gradient at each point, what we can do is draw a tangent. So let's say this is x is equal to minus 5, let's say, right? What we can do is draw a tangent to the curve at that point, and a tangent is just a straight line that touches the curve at that particular point. So let's say that's our tangent. Imagine that's a straight line, and let's say this is where x is equal to 2, and that's our tangent. Let's say that's what the tangent looks like. It's not perfect, but the idea is that these two tangents obviously have different slopes. This one's clearly negative, this one's clearly positive. And of course, if you draw a tangent at this point, it's going to have a different slope than any of these two tangents. So how can we know what the gradient is at that point? Well, we use something called derivatives. Derivatives. And what we have is a power rule. This is the easiest way to take derivatives. Power rule. So let's say we have, let's use this function, yeah. Let's say we have y is equal to x squared plus 2x minus 3. So how do we find the derivative? Or you could say derivative, you can remember this as like the gradient function. Because all the derivative does is it gives you the gradient at a certain point on the curve. So the way you take the derivative is you see the power on x squared. That's 2, right? This is 2 right here. So you do 2, you multiply it by the coefficient of x squared, which is just 1, because nothing there means just 1. So that's 1. And then you have x squared again, but then you reduce the power by 1. So you make it 2 minus 1. And then you add that, and then you do the same thing for the second term. So you have, so the power on x here is just 1. So you have 1 times the coefficient of 2x is just 2. And then x to the power 1 minus 1 again. Minus 3 times, okay, so this is nothing here, which is the same as x to the power 0. That's what the power is. So you can do 3 times 0, x to the power 0 minus 1. Of course, this is going to cancel out. So we'll have 2 times 1 is 2, times x to the power 2 minus 1, which is just 1. So we have 2x, plus 2 times 1 again is 2. X to the power 1 minus 1 is x to the power 0, which is just 1. So plus 2 times 1. And then this is minus 3 times 0. So this is just 0. So we don't need to add that. And then you're left with 2x plus 2. So the gradient function is equal to 2x plus 2. But gradient function is a long word, and instead of saying that, we just say dy by dx. Or you'll see written as y prime, or you might see written as f prime of x. All of these mean exactly the same thing. This means take the derivative of the function that you have. Alright, so let's do a worked example and it'll make more sense. So we have the question, f of x is equal to x cubed minus 3x squared minus 4. Find the gradient of the graph of y is equal to f of x, where x is equal to 1. Well, we know how to find the gradient, right? The gradient function is just dy by dx. which is also the same as f prime of x. Well, we know what to do now. Let's start with x cubed. So we have 3 right there. So we put the 3 in front, multiplied by the coefficient of x cubed, which is just 1. So that's 1. And then x to the power 3 minus 1. So that would just be 2. Minus, well, we take the power again. That's 2. The 2 comes from here. Take the 2. Multiplied by the coefficient, which is 3. And then x to the power 2 minus 1, which is just 1. And then minus 4, and then of course this is x to the power 0 again, as we said. So this is 4 times 0, x to the power 0 minus 1. We don't need to worry about this because it will cancel out. And we're left with f prime of x, which is the gradient function, is equal to 3x squared minus 6x to the power 1, which is just minus 6x. Find the gradient where x is equal to 1. Well, so you put 1 instead of x squared here, and you put 1 instead of x over here. So you're left with 3 times 1 squared minus 6 times 1. That's just 3 minus 6, which is negative 3. So look, instead of drawing the whole curve, which would probably look something like, I don't know what it looks like. Let's just say it's a cubic, so it looks something like that. And you'd have to find x is equal to 1, and you'd have to draw the tangent, and you'd have to make sure that your tangent is precise as well. And then you'd have to make sure that you calculate the gradient. Instead of doing that, we can just take derivatives and get the actual answer, which is correct and much cleaner. Find the coordinates of the turning points of the graph y is equal to f of x. Okay, so what are turning points? So, by the way, if you hear turning points, stationary points, critical points, all of them mean the exact same thing. So, turning point. So let's say we had a curve that looked like this. Let's say we had a curve that looked like that. You can see at this point right here and this point right here, right? Let's say we wanted to draw a tangent at those points. Well, the tangent would just be a horizontal line, right? It's a horizontal line. It's a horizontal line. What does a horizontal line mean? We know this from, previous work with lines. Horizontal line means, well, it just means that the slope or the gradient is equal to 0. But we know how to get the slope. The way to get the slope is by taking the derivative. Well, we already took the derivative. Our derivative is 3x squared minus 6x. And it has to equal to 0 at the turning point. Well, it's equal to 0. That's it. That's all you have to do. And now you just have to solve this equation for x. Well, you can divide by 3, so you're left with x squared minus 2x equals 0. And then you can factorize. You have x minus 2 equals 0. We can have x is equal to 0 or x is equal to 2. And then you have to find the coordinates, right? So you put x is equal to 0 back into the function f of x. So you put it back into this function right here. So you would have 0 cubed minus 3. 0 cubed minus 3 times 0 minus 4. I think that's what the function was. Yep, minus 3 times 0 squared minus 4, which is just negative 4. And then when x is equal to 2, you would have 2 cubed minus 3 times 2 squared minus 4, which is equal to 8 minus 12 minus 4, which is equal to negative 8. But that's it. Those are your coordinates. You have 0 and minus 4, negative 4. And then you have 2 and negative 8. And you have to make sure that you match the correct coordinates. You can't do 2 and negative 4. You can't do 0 and negative 8. You have to make sure that you match what's happening. Let's do a bonus section actually. Let's call this bonus. So we know how to take derivatives. We know what they do. They give us the gradient at any point. And we know that can help us find the turning points on a curve. But what if you want to know if the turning point is a maximum or a minimum, right? Well, in this curve, it's pretty simple. You can see this is like a maximum point because it's pretty high up. This looks like a minimum point because like at the bottom. But what if the curve was more complicated and we couldn't draw it? How would we know how to get the nature? It's called the nature. How would we know what the nature of the stationary point is? Well, what we do is we take the second derivative. So you write it as d squared y by dx squared. That's just the notation. Or you could write y prime prime or f prime prime of x. And all it is, yeah, you just take the derivative of the derivative that you already have. So in our case, our derivative was 3x squared minus 6x. So we have to take the derivative of 3x squared minus 6x. Well, that's pretty simple. We know how to do this. So we do 3 times the power 2 right here times x to the power 2 minus 1, which is 1, minus 6 times 1, which is the power here, times x to the power 1 minus 1, which is 0. And you're left with 6x minus 6. And now what we do is we put our x coordinate back into the x over here. So we put it back in. So now we have 6 times 0 minus 6, which is obviously negative 6. And then we have 6 times 2 minus 6, which is positive 6. That's a 0. And this is just something you have to remember. Maybe a proof will be in a different video, but if the second derivative, so this is the second derivative, right? If it is less than 0, then this is a maximum point. You have to remember this. And if it is greater than 0, then it is a minimum point. Something you have to remember. If it is equal to 0, then it's called an inflection point, but I don't think we need to worry about that right now. It's called a point of inflection. But honestly, don't really think about this. We don't need this right now. We just need this, and we need this. So now we don't even know what this curve looks like, but we know 2 things about it. We know it has 2 turning points at 0 and negative 4. So let's try to draw this curve, even though we don't know what it looks like. Let's make it cleaner. So 0 and negative 4, there's a turning point there. And 2 and negative 8, there's a turning point there. So that's 2, that's 0. Well, we know the point at 0, negative 4 is going to be a maximum, right? Because when you put 0 and you go to a negative number, and that means maximum. So that means it's going to look something like, it's going to be coming upwards at this. And then since 2 was a minimum point, that means it will be going downwards at this point. And since it's a cubic, it has this type of shape. So we know it's going to look something like that. And we have a pretty good sketch of this curve, even though we have no idea about anything related to this curve. But still, by just getting the turning points, we can draw a pretty good sketch of this curve. And if you draw the actual curve on, let's say, GeoGebra or whatever website you use, you will see it looks similar to this. There's going to be an x-intercept somewhere over here, but we don't know what it is. We don't need to find that right now. So in conclusion, what have we learned? So we have, let's write over here. So we know about derivatives. That's the main thing. We know that it's basically the gradient function. Gradient function. We know how to calculate it using the power rule. Power rule. We know about turning points or stationary points, critical points. And the bonus section that if you stayed for, you learn about the nature of turning points. You know about nature of turning points and derivatives, gradient function, power rule, and that's all you need to know for an introduction to differentiation. And the chain rule. So before we start, let's remember something. So remember the power rule, right? So let's say you want to find the derivative of negative 5x. Well, we said that is just negative 5, and this is x to the power 1. So you bring the 1 in front, and then x to the power 1 minus 1, which is equal to negative 5 x to the power 0, which is equal to negative 5. This is just the power rule. Remember this. The important thing that I want to notice here is that if you did instead negative 5 times the derivative of x, right? This would be the same as negative 5 times, well, this is x to the power 1, so you bring the 1 in front, 1, and then x to the power 1 minus 1, which is 0, which is equal to negative 5 as well. So multiplying by a constant, if it's positive or negative, does not change the outcome of what the derivative is going to be. So I wanted to get that clear. And let's take trigonometric derivatives. So far we've been dealing with polynomials. A polynomial is like x squared plus 3x minus 5 plus 2 over x. These are all polynomials. But what if we had the function y is equal to sine of x? Because this is also pretty common. Trig functions are very common. Let's start with sine of x. Okay, how should we do it? Let's think about it before I give you the answer. So let's draw y is equal to sine of x. Let's remember what it looks like. So we have y-axis, we have the x-axis here. And I'm gonna need a few angles. I'm gonna need 0, I'm going to need 90, I'm going to need 180, I'm going to need 270, and I'm going to need 360. I'm going to draw a rough sketch. Sine starts with 0, reaches 1 at 90, and then goes down to 0 here. It's meant to touch 0, so we'll draw that again. So goes up, comes down, touches 0, goes down to -1, comes back up, goes back to 0. So this is 1, and this is -1. This is just y is equal to sine of x, right? This is sine of x. Now let's do something. Let's draw another graph, and what this graph will be, I'll show you what this graph will be. We'll have 90, 180, 270, and 360. Okay, let's do 1, and let's do -1. Now, I want you to look at the derivative of sine at 90. If you draw a tangent to sine at 90 degrees, you'll see it's a horizontal line. That means the derivative is 0. So let's put the point 90 and 0 over here. And I want you to draw the tangent to the line at 270, and again, of course, the derivative is 0. So put another point at 270 and 0. Now, if you want, and this is a good exercise for you, you can draw a tangent to the sine graph at 0. So you can draw a tangent like that. And if you calculate the gradient of this tangent, you'll see it's equal to 1. And if you calculate a gradient at 180, let's say you draw a tangent here, and then you calculated that gradient, that would be -1. So we have another point here. And then at 360, if you drew another tangent and calculate the gradient, I'm telling you it's going to be equal to 1 again. I would do it, but then there's not enough space to draw proper tangents and do it properly. So let's connect these points together. What do we get? We get something that looks like this. We get a graph that looks like this. And this is the graph of the values of the tangents of sine of x at different angles. But this is a very familiar graph. This is actually y is equal to cosine of x. So what does that mean? That means that the derivative of the sine of x is actually equal to the cosine of x. That's an interesting relationship that we have. We never thought of sine and cosine as being derivatives, as the cosine of being the derivative of sine. And you can do the same exercise again. So now you have cosine of x here. You can draw a tangent over here. It's going to be 0. You can draw a tangent here. You can draw a tangent here, 270 and 360. And we're not going to do that, but I'm just going to write down the answer. And you would think it would be the sine of x. The derivative of cosine would be the sine of x. And you would be almost correct. It's actually equal to the negative of the sine of x. Yep, just have to remember that. It's going to be negative here, but with sine, it's just going to be positive cosine of x. What will be the derivative of negative sine of x? Well, we said that we don't really care about the negative sign. We can just get rid of it for now, so we can just put the negative in front. And then we can take the derivative of the sine of x. But we already know what that is. That is the cosine of x. So from negative sine of x, we have negative cosine of x. Let's take the final derivative. Let's take the derivative of negative cosine of x. And what do we get? Well, we don't care about the negatives, so we can put that in front. And then derivative of cosine of x is negative sine of x. So negative sine of x, which is equal to positive sine of x. And we don't need to take any more derivatives because we can just repeat the cycle now. So sine goes to cosine, cosine goes to negative sine goes to negative cosine goes to positive sine, and then you can repeat this cycle. Just for the sake of having it, I'll put the derivative of tan of x, and that is equal to secant squared of x. Just in case you were curious, we'll show why this is true in another video on the quotient rule and product rule, but secant squared is just 1 over cosine squared of x. I just thought I'd mention it just in case you're curious, but we don't really need to worry about this right now, so might as well cancel it. Alright, we did trig derivatives. Now let's focus on the chain rule. So this is probably the most important rule when it comes to differentiation. So let's say you had y is equal to sine of 2x. How would you find the derivative of this? So what's dy by dx equal to? Well, we now have to find the derivative of sine of x, which is equal to cosine of x. But this is sine of 2x, so would it just be cosine of 2x? Let's put cosine of 2x. Question mark? Is that a valid guess? And you're almost correct, but let's think about it in a better way. So we're going to abuse some notation here. So we have dy by dx, right? Let's introduce a function t. Let's say t is equal to 2x, right? Because we have 2x here, let's call it t is equal to 2x. So now we have y is equal to sine of t, right? So far we haven't really done anything. It's just calling t equals 2x because we don't want the 2. So t is equal to 2x. Now what if we take the derivative of x with respect to t? So dt by dx. So we just take the derivative of x. That's all this is saying. Well, we don't have to do that. Take the derivative of 2x. That's just 2 times x times 1 times x to the power 1 minus 1, which is equal to 2. So we have dt by dx is equal to 2. And what's the derivative with respect to t of y? Let's say dy by dt. So like of this function right here. Well, that is simple. That's just cos t, right? If you remember, here we did derivative of sine of x is equal to cosine of x. If you replace x with just t, you will get dy by dt is equal to cos of t. Now, but we need dy by dx, and we don't have dy by dx over here anywhere. We have dt by dx, and we have dy by dt. But what if we did something? What if we did dy by dx is equal to, let's think, we can work with fractions. What if we did it as dy by dt times, this is multiplication, dt by dx? What if you did that? Well, you can see the dt here would cancel out, right? And we would be left with dy divided by dx. Well, that's what we need. We need dy by dx. So let's try it. Let's try dy by dt. So dy by dt is cosine of t. We have that. Times dt by dx, which is equal to, we found that over here is equal to 2. So multiply that by 2. And you're left with 2 times cosine of t. But you have to remember, you can't write it in terms of t because we're asking dy by dx. You need it in terms of x. But we know what t is. T is equal to 2x. So now we just put it back in. So you're left with 2 cosine of 2x. And that's it. Dy by dx is equal to 2 cosine 2x. We estimated it would be cosine 2x. We didn't know how to do it, and we were pretty close, but this 2 is very different. This 2 cosine 2x is very different from just cos 2x. And the chain rule is so important because let's do a harder function. Let's do y is equal to 4x plus 3 to the power of a half. Let's say we have that. How would you find the derivative of that function? Like, we don't know how to do that. That's insane. But we know that, let's say y, like we can let t equal 4x plus 3, right? So now we have y is equal to t to the power of a half. Well, we need two things. Well, what we really need is dy by dx. That's question mark. But we don't know how to get that. But what we can get is we can get dy by dt. And we can get dt by dx. Well, dy by dt is equal to, if you multiply these two, you would get dy by dx. dy by dt is equal to, take the derivative of this function right here. So you have a half in front, because the half goes here from the power rule, times t to the power of a half minus 1, which is negative a half. So you have that there. And then you have dt by dx, which is equal to, let's actually do it on the left side. You have dt by dx, which is equal to, well, t is just 4x plus 3, so we just do the power rule on x now. That's 4 times 1 times x to the power 0, which is just 1, plus 3 times 0, x to the power 0 minus 1. Well, this cancels out, of course, and you're left with just 4. Well, now we know what to do. dy by dx is dy by dt times dt by dx. So we have dy by dx is equal to 4 times, and what's dt? So we just did dt by dx times dy by dt is the same thing. You change the order around. And dy by dt is a half t to the negative a half. Well, remember, it has to be in terms of x, but we know what t is in terms of x, so we can do 4 divided by 2 straight away. We have 2, and then t is just 4x plus 3. So you're left with 4x plus 3, and then a negative a half up there. And that's it. That's the derivative of this function right here. We would have no idea how to do this, but as soon as we let t equal to 4x plus 3, we take the derivative of x with respect to, we take the derivative of t with respect to x, we get just 4 right here. And we take the derivative of y with respect to t, and we get a half times t to the power negative a half. Multiply them together, you end up getting 4 times a half times t to the power negative a half. 4 divided by 2 is just 2. And we already know what t is. T is 4x plus 3. Put 4x plus 3 back in, and the negative a half power, and that's the derivative. Alright, let's do one final example. Let's say we have y is equal to, let's put everything that we've done together. We have 4 sine 2x plus x all cubed. How do you find the derivative of this function? So we need dy by dx. Question mark. Well, so we need two things. We need dy by dt, and we need dt by dx. This x right here is multiplication times dt by dx. Well, as you've noticed by now, we just let t equal the thing inside the brackets usually. So we can let t is equal to 4 sine 2x plus x. So now y is equal to t cubed. Let's do dy by dt first, because that's pretty simple to do. So dy by dt is just the simple power rule that we know. So that's just 3 times t to the power 3 minus 1, which is 2. So we have 3t squared. Okay. Now dt by dx, how would you do that? Dt by dx is equal to 4 sine 2x. Well, we know, let's just deal with 4 sine 2x first. We can worry about the x later. This is very easy, but 4 sine 2x is more difficult. Well, we know it doesn't matter if you multiply by a constant, so we just put 4. And then we take the derivative of sine of 2x. Well, we already took that, right? We found that to be sine of 2x. We took the derivative, found that to be 2 times cos of 2x. We can put that back in. So now we have 4 times 2 cos 2x in brackets, and then plus the derivative of just x to the power 1, which is 1 times x to the power 0, which is just 1. We have dt by dx, and we have dy by dt. Now we multiply them together. So now we have 3 times t squared times this whole thing. So you have 8 cos 2x plus 1. But we know what t is. We let t equal 4 sine 2x plus x. So now, this is dy by dx. We can't just leave it in terms of t because we want it in terms of x. We're doing it with x right here. So that is actually equal to 3 times, and it's multiplication, so I can just put 8 cos 2x first. 8 cos 2x plus 1. And then times t squared. Well, t is 4 sine 2x plus x. And then this thing is all squared. This bracket is squared. Let me just draw the brackets nicely. That and that. And that's the derivative. So if you want to write it very clearly, you can write 24 cos 2x, because 3 times 8, 24, plus 3 times this whole thing right here, 4 sine 2x plus x, and this bracket squared. And that's dy by dx. So you can see how important the chain rule is. This looks like an impossible derivative to take, but it's actually very easy. So we let t equal a function inside the bracket usually, and we find dy by dt, which is it's always going to be very simple if it's a power, so that's 3t squared. And then we find dt by dx, which in this case we had to use our trig derivatives, but that was very easy. And actually this right here, this 2 cos 2x, is also actually the chain rule. So, because if you remember from here, the way we found the derivative of this was we used the chain rule here as well. So what we've done actually is we have used the chain rule 2 times to find the derivative of this function right here, of y is equal to 4 sine 2x plus x, all cubed. So you can see how important the chain rule really is. And you can simplify this and you're left with this. One important thing I have to mention, I cannot like stress this enough, is make sure your answer is in terms of x and not t. So you have to make sure you put x back into where t is. Otherwise, you will not have the right answer because it's it's dy by dx. It's not dy by dt. So what have we learned today? So we've learned about trig derivatives. We've learned about chain rule. Honestly, that's all we've learned, but we have learned how important the chain rule actually is. Because you're taking derivatives of things that you don't even know what this looks like. You don't know what 4 sine 2x plus x cubed looks like. But if you want to find the gradient of it for any reason at all, and obviously turning points, and there are many applications of differentiation, but you can just take the derivative and imagine having to draw this curve right here. That is an insane curve to draw. I don't even know what it looks like. But if you just take the derivative of it, then you're good. You can find out all the things that you need to know, and you'll be good from there. So yeah, we've learned about trig derivatives, we've learned about chain rule, we've learned about how important the chain rule is. And yeah, that's it. I do want to make a video on the quotient and product rule, and we're going to go over why the derivative of tan of x is equal to the secant squared of x. So yeah, keep a lookout for that. Yeah, like, comment, subscribe, and yeah, let me know what you want to see actually. About the product and quotient rule. So we'll start with the product rule. And unsurprisingly, it's related to derivatives, and it's exactly what you would expect. It's when you have a function f and g, and you multiply them together, and then you want to take the derivative of that whole thing. What do you get? Well, you get f prime g plus f times g prime. And quotient rule, again, unsurprisingly, is when you want to divide. Let me write that q better. Q. Okay. And the quotient rule, unsurprisingly, is when you want to divide two functions and then take their derivative. And this is a bit more unexpected. Like, you wouldn't really expect this formula, but it is true. And again, I won't give a proof of it, but I will show how it works. So if you want to take that derivative, that is equal to I think this is it. Yeah, this should be correct because it's easy to get confused here. So you can see this is the exact same, but then a subtraction sign instead. And then all of that divided by g squared. Let me just make a note. F and g are just functions. Any functions of x. That's it. So let's look at the quotient rule first, actually. And let me show you why the derivative of tan of x is equal to the secant squared of x. Let's see why that's true, because I did promise we will see it in one of the videos. The derivative of tan of x. So that's the same as taking the derivative of sine of x divided by the cosine of x, right? That's pretty simple. Well, we can use the quotient rule now. So the quotient rule says f over g. So f in our case is sine, g in our case is cosine. So we do f prime times g. So f prime is just the derivative of sine, which is cosine. So that's cosine of x times g, which is cosine of x. So that becomes cosine squared of x, minus f, which is just sine of x, times g prime, which is derivative of cosine, which is negative sine. So this is sine times negative sine of x, is in brackets, and then divided by g squared. So that's basically cosine squared of x. Well, you can see you have a negative and a negative, so that becomes a positive. So then you basically get cosine squared of x plus sine squared of x divided by cosine squared of x. Well, we know cosine squared of x plus sine squared of x is equal to 1. That's a very famous identity that you should know. And then 1 divided by cosine squared of x, well, we know that's the same as 1 divided by cosine of x all squared, because 1 squared is just still 1, and that is equal to the secant of x all squared. Secant of x is just 1 over cosine x, and this is equal to secant squared of x. So that means that the derivative, we started at the derivative of tan of x. So that means the derivative of the tan of x, or the tangent of x if you want, is equal to secant squared of x. And that's why this is true. I did mention this in one of the videos, I think in the chain rule video, and now you can see when you use the quotient rule, this turns out to be true. Now let's do the easy one. Let's do a product rule example. So let's say we had to find the turning points. So find the turning points of y is equal to, let's make it difficult. Let's make it 2 sine 2x cosine 2x for x between 0 and 180. Well, 180 is just pi. Let's work in radians. So that's between 0 and pi radians. Let's find the answer of that. Let's find the turning points. Turning point, and then s, just in case there's more than one. So, well, we use the product rule again, right? So we have that 2 in front. We don't really care about the constant 2. So that's 2. And then we take the derivative of sine 2x times cosine 2x. Well, if you remember from this slide right here, you take the derivative of the first function multiplied by the second function, and then you add that to the first function times the derivative of the second function. Well, then you have, so let's take the derivative of sine 2x first. That's 2 cos 2x. And then you multiply that by cosine 2x. That becomes 2 cosine squared 2x. And then you add that to sine 2x times the derivative of cosine 2x, which is negative 2 sine 2x. I covered these derivatives in our trig and chain rule video, so you should go watch that if you don't understand what's going on over here. So you get that, and then that big 2 is just outside. Well, if you're finding turning points, then the derivative must equal to 0, right? This is dy by dx. And since it's a turning point, it should equal to 0. Well, we can get rid of the 2 because 0 divided by 2 is just 0. So now we have 2 cosine squared of 2x minus 2 sine squared of 2x is equal to 0. Well, we can factorize the 2 again, so we have another extra 2. So you're left with, and cosine squared 2x is actually equal to 1 minus sine squared 2x, because sine squared plus cosine squared equals 1. So you're left with 1 minus sine squared 2x minus sine squared 2x is equal to 0. You can bring the sine squared 2x to the other side, so you're left with 1 is equal to 2 times sine squared 2x. Well, this is pretty simple to solve, so you're left with a half is equal to sine squared 2x. If you take the square root of both sides, then you're left with the sine of 2x is equal to plus or minus, of course, root 2 over 2. Let's write that better. Plus or minus square root of 2 all divided by 2. Well, take the sine inverse on both sides, so you're left with sine inverse of the sine of 2x, which is just 2x, is equal to, well, let's use a calculator, right? So we're working in radians, so root 2 over 2. If you take the sine inverse of that, you should get a couple angles. What I got in my notebook is you should get pi over 4. That's one of the angles. And then you should get 3 pi over 4. That's the other angle. You should get negative pi over 4. You should get negative 3 pi over 4. And you should get 9 pi over 4. And so on and so forth. But I'll tell you, we have negative pi over 4 and negative 3 pi over 4. And those aren't in our domain between 0 to pi. But if you have negative pi over 4 as one of the answers, then we have negative pi over 4 plus 2 pi as one of the answers. And we also have negative 3 pi over 4 plus 2 pi as one of the answers. This is equal to 2x. So we actually will have 4 answers in our domain. So we have x is equal to, well, pi over 4 divided by 2 is pi over 8. 3 pi over 4 divided by 2 is 3 pi over 8. And then negative pi over 4 plus 2 pi is actually 7 pi over 4 divided by 2 is going to be 7 pi divided by 8. And negative 3 pi over 4 plus 2 pi should be 5 pi over 4. And then divided by 2 would be 5 pi over 8. So we have 4 turning points. We have pi over 8. And you can put these numbers back into y is equal to 2 sine 2x cos 2x. And you'll get these numbers. And I'll also put a graph up if I can edit properly. And it will show you that these are the correct values for y, for the turning points. So you have 3 pi over 8, and you have negative 1. Then you have 5 pi over 8, and you have positive 1 again. And you're going to have 7 pi over 8, and negative 1 again. So those are our 4 turning points for y is equal to 2 sine 2x cos 2x. Alright, let's do an example question. So the diagram shows the curve of the equation y is equal to e to the negative a half x times x squared minus 5x plus 4. The curve crosses the x-axis at the points a and b and has a maximum point c. Find the exact gradient of the curve at b. That's part A. Okay, that's not that bad. So let's find the coordinate of b first before we find the gradient. So the curve intersects the x-axis at 2 points, at a and b. That means at that point y is equal to 0. So 0 is equal to e to the negative x over 2 times x squared minus 5x plus 4, right? Well, this has no solutions. If this is equal to 0, there's no solution, so we don't need to worry about that. And you'll see that y in the logarithms video. So now you're left with x squared minus 5x plus 4 is equal to 0. You can factorize this. You can have x minus 4 times x minus 1 is equal to 0. So either x is 1 or x is 4. Well, you can see it crosses the x-axis at 2 points, at 1 and 4. And obviously 1 comes before 4, so A has to be the point 1. So A is actually 1, and B is 4. And we have to find the exact gradient. So to find the gradient, we just take the derivative, right? So we find dy by dx. And you can see this is a product of two functions. If we let f, let's do it on the side. If we let f equal e to the negative a half x, and g equal x squared minus 5x plus 4, well, then you're taking the derivative of a product of two functions. Well, we know what we do. We take the derivative of the first function, so we take the derivative of that, which is negative a half times e to the negative x over 2, and we just multiply it by whatever the other function is, so just x squared minus 5x plus 4, and then we add that to, we leave the first function however it is, so it's e to the negative x over 2, times the derivative of the second function, which is just 2x minus 5. This is using the power rule, of course. Well, you can see e to the negative x over 2 is common in both of these terms. So we have e to the negative x over 2. You can factorize that. And then you have negative x squared over 2. Just bring the negative a half inside here. So then you have plus 5x over 2 minus 2 plus, I'm just doing 1 times 2x minus 5, so you're left with 2x minus 5. And we have to find the gradient where x is equal to 4. So you're left with e to the power negative 4 over 2 is negative 2 times negative 4 squared over 2 is negative 8 plus 20 divided by 2 is 10 minus 2 plus 2 times 4 is 8 minus 5. And that is just 3 e to the negative 2, which is equal to 3 divided by e squared. And that's the gradient of this curve at point B. Find the exact coordinates of C. So we're told here that it has a maximum point at C. Here, it has a maximum point. But we have to also remember, if you just find the derivative of this and calculate the turning points, we'll also get a value over here. But we don't need this value. We do not need this value right here. So we have to make sure we're careful about that. So to find the exact coordinates of C, well, we just take the derivative again. We don't even have to, we already have the derivative. It's just equal to this, right? We already found the derivative. So we have e to the negative x over 2 times negative x squared over 2 to plus 5x over 2. Yep, plus 5x over 2 minus 2 plus 2x minus 5. Minus 2 plus 2x minus 5. And this is equal to 0 because we're finding a turning point. Well, once again, let's see that this bracket is equal to 0 or this is equal to 0. Well, this is never equal to 0. Again, in the logarithms video, you will see why. So you're left with negative x squared over 2 plus 5x over 2 plus 2x, and then minus 2 minus 5 is minus 7 equals 0. Well, we can multiply both sides by 2, so you're left with negative x squared plus 5x plus 4x minus 14 is equal to 0. And then you can bring x squared to the other side and everything else to the other side as well, so you're left with x squared minus 9x plus 14 is equal to 0. It's a simple quadratic to solve. You can factorize it. X minus 2, x minus 7 is equal to 0. So x is equal to 2 or x is equal to 7. Now which x do we use? Well, remember, there are 2 points. There's a minimum point right here, and of course that point is 2 because it's between 1 and 4, so that has to be x is equal to 2. So this is actually 2, and that means that we don't really know, but this is definitely 7. It makes sense. It comes after 4, and it looks like if this is 4, then this does look like it would be 7, considering the scale of this curve. So x is equal to 7 is what we have to use. This is important. Well, you just put it back into the function right here. So you're left with the exact coordinates are 7 and e to the negative 7 over 2 times 7 squared is 49. Was it plus 5x? it's minus 5x plus 4. So minus 5 times 7 is 35, and then plus 4, which is equal to 7. And then this is 49 minus 35 plus 4 is 18. So just 18 times e to the power negative 7 over 2. And once again, if I edit it correctly, I will draw this curve, or I will tell the GeoGebra to draw this curve for me, and you will see that this point is actually 7, and then the value of that is 18 times e to the power negative 7 over 2. So yeah, that's the quotient rule and the product rule. Very simple. Just a quick recap. So fg prime is equal to f prime times g plus f times g prime, and f over g prime is equal to f prime g minus f g prime all divided by g squared. So yeah, those are the two things you need to know, and you've seen why they can be useful. You can take derivatives of these type of functions now. You can actually take any derivative now. Now you have all the ways to take derivatives. So yeah, apart from like special functions, you should know how to take derivative of any polynomial function at the very least now, no matter how difficult it looks. So yeah, that's the product rule and the quotient rule. Alright, so let's talk about parametric derivatives. So now we're getting into the serious differentiation. So let's say instead of having y is equal to something in terms of x, right? We're used to something like this. We're used to like y is equal to sine of x, or y is equal to x squared. Instead of having that, let's say we had y is equal to t squared. And then we need something for x, so let's say we had x is equal to t to the power 4. Let's say we had that, right? Because we can't give y in terms of x. Let's say it was a more complicated function, and it was difficult to give y in terms of x. So we can give y in terms of a parameter t, that's what a parameter is, t, and then x in terms of the same parameter, t. So you can, if you try to sketch this, you could take different values for t. So you could take t is equal to 0, and then plot the point 0 and 0 on the curve. If you take t is equal to 2, then you would have x is equal to 2 to the power 4, which is 16, and y is equal to 2 squared, which is 4. So you would plot the point 16 and 4 on the curve, and then you can take all the points for t, and then you can have a curve for x and y. But we're not worried about plotting the curve, we're worried about getting the derivative. So how do you find dy by dx for that curve when you do plot it? Well, there are two ways to do it. One way is, you can see if you square this right here, you would get y squared is equal to t to the 4, right? Because if I square all of this, then I get y squared is equal to t to the power 4. And t to the power 4 is also equal to x, so you get y squared is equal to x. And then y is equal to x to the power half. And then you can take dy by dx from here, and you would end up getting a half times x to the power negative a half, which is equal to 1 over 2 square root x. So you can do it that way, but if the function is more complicated, then there is no way you're going to be able to arrange y in terms of x that easily. So let's see if we want to do it using t's. So remember, dy by dx, what was the chain rule? The chain rule was dy by dx is equal to dy by dt times dt by dx. Well, we can use this. So dy by dt, we can find that very easily from our original function was y is equal to t squared. Let me just write it again because I wrote on top of this. So y is equal to t squared and x is equal to t to the 4. So we can find dy by dt very easily. We can't find dt by dx, but what we can find is dx by dt, because you can just use the power rule on this right here. So let's do that first, and then we'll see why that's useful. So dy by dt is equal to 2t. That's easy. And dx by dt is equal to 4t cubed. Right? Pretty simple. Now let's be smart about this chain rule. So we are multiplying two fractions, right? But isn't that the same as doing dy by dt divided by dx by dt? Because then if you divide two fractions, then you can multiply by the reciprocal. And the reciprocal of this is dt by dx, which is what we which is what we need to get dy by dx. So what if we did that? Is that equal to dy by dx? Yes, it is, because the dt's will cancel out. So let's do it. We have dy by dt and we have dx by dt as well. So we have 2t divided by dx by dt is 4t cubed. And that leaves us with, cancel the t, you're left with 1 over 2t squared, which is actually equal to, well, remember over here we go 1 over 2 square root x. What is the square root of x actually equal to? If you take the square root on both sides, then you end up getting x of square root of x is equal to t squared. And t squared is right here as well, so you actually end up getting 1 over 2, let's write that better, you end up getting 1 over 2 times square root of x. So you can see why this works. And it worked in our case over here. This was very easy to do using the normal method of just rearranging and then finding y in terms of x, because these are very simple. What if you had a way more complicated function? Let's say you had something like y is equal to sine t plus 2t, and then x is equal to 1 over cos 2t. This will take you like so long just to get y in terms of x, and then to find the derivative of that would be so complicated. Instead, we can take the derivative of y with respect to t first, and the derivative of x with respect to t, and then just divide them by each other, and you'll end up getting dy by dx. That's like an introduction to parametric differentiation. Let's do a question for parametric differentiation, so it makes more sense. It's question 4. The parametric equations of a curve are x is equal to cos theta over 2 minus sine theta, and y is equal to theta plus 2 cosine theta. Show that dy by dx is equal to 2 minus sine theta all squared. Okay, we know how to find dy by dx. So we need dy by dt divided by dx by dt. So we just have to take derivatives. Instead of t, we're doing theta, so it's the exact same thing. So let's do dy by d theta. Well, that's just 1 minus 2 sine theta. Right? That's just the derivative of theta plus 2 cos theta. Derivative of theta is 1. The derivative of 2 cosine theta is minus 2 times sine theta. So we have dy by d theta. That was simple. Let's find dx by dt. That's a bit more complicated. And here we'll have to use the quotient rule, if you remember from last time. So what do? So we take the derivative of this, which is negative sine theta, multiply it by 2 minus sine theta. And then from there we subtract the numerator, which is cosine theta, multiplied by the derivative of the denominator, which is negative cosine theta. And then of course all of this is divided by the denominator squared, which is 2 minus sine theta squared. 2 minus sine theta all squared. Okay, so we have a start. So what do? Let's simplify this first. So you can see you'll have negative 2 sine theta plus sine squared theta plus cos squared theta in the numerator. So that's actually equal to, well, sine squared plus cos squared is just 1, right? So you have 1 minus 2 sine theta in the numerator, and that's divided by 2 minus sine theta all squared. Okay, also this is, of course, all of this is also 2 minus sine theta all squared. So what can we do now? So we do dy by d theta divided by dx by d theta. Dx by d theta. I wrote a t over here, but I meant theta. It's the exact same thing, just choosing what variable you want. There's no difference. So let's do it. So we have dy by d theta, which is 1 minus 2 sine theta. So you have 1 minus 2 sine theta. And you're dividing it by, this is dy by dx now. So you have dy by d theta divided by dx d theta. So if you're dividing by this right here, then you would do the reciprocal of this and multiply it. So you'd end up getting times 2 minus sine theta all squared divided by 1 minus 2 sine theta. But you can see now you have 1 minus 2 sine theta in the denominator and the numerator. So they just cancel out. So you're left with dy by dx is equal to 2 minus sine theta all squared. So you can see you end up getting the correct answer. That's what you have to show. Now, arranging x in terms of theta and then putting that in for y, that's going to take very long because I don't even know if you can separate this that easily. So that's going to take so much longer, and to find the derivative will be even more complicated because you will have a very weird looking function over here. Instead, you can use parameters and just find dy by dx using the chain rule, and you end up getting a pretty simple answer. Oh yeah, that's it. There's no part B. So yeah, that's really all you need to know about parametric derivatives. So let's do one more example. Let's make our own example. Let's say we had y is equal to sine t and x is equal to cosine t. What's dy by dx? Well, we need to find dy by dx. Well, we have dy by dt, right? dy by dt is equal to the derivative of sine t, that's cosine t. And then dx by dt is equal to the derivative of cosine t, which is equal to negative sine of t. Right? So now we have to find dy by dx. So we do cosine t divided by negative sine t. So you're left with cosine t divided by negative sine t. This is dy by dx. Well, that's basically negative cotangent of t. Right? Because cosine over sine is 1 over tangent, and then you have the negative, so it becomes negative cotangent of t. Or you can write that as negative 1 over tan t. We can do more examples if you want, but I don't think we should do it anymore because it's really very simple. You have it in terms of the parameters, you find the derivative of each of them, and then you just divide them by each other, and you should get the right answer. So yeah, that's parametric differentiation. Okay. So what is implicit differentiation? So what does implicit mean? So usually we're used to functions like y is equal to x squared or y is equal to sine x. And these are called explicit functions. And a simple way to think about it is by thinking that you can separate y on one side and everything with x on one side. But let's say you had something like x to the 4 plus xy plus y squared is equal to 0. How do you separate this equation? Or something more difficult than this. Let's say I gave you sine of xy plus xy squared is equal to 0. How would you separate these equations? It would take a lot of time and you'd have to be very careful with what you're doing. So these are called implicit equations because you can't really get x on one side and y on the other side. You can't get y in terms of x. Over here, y is in terms of just x. Here, y is in terms of just x. But here, x and y both combine to give you something else. It doesn't have to be equal to 0, by the way. It can be equal to something else. It can be x4 plus xy plus y squared equals 25, for example, right? And let's say you had a function like this, and let's say you plotted, right, different values of x and y. And now you want to find the derivative, of course. So how would you find the derivative of this? So let's think about it a little bit, because this can be a bit tricky. So let y equal f of x, right? Let's just get that down there. So now a new equation is x to the power 4 plus x times f of x plus f of x all squared is equal to 25. Now what do? Now we try to take the derivative on each side. So we take the derivative, so d by dx of this side, and that should be equal to the derivative. Let me write that better. It's a bracket. And that should be the derivative of this side as well, because we have to do the same operation on both sides. But derivative of 25 is just 0, right? We know that. So we'll just leave that out for now. So the derivative of this thing right here, how would you do that? Well, x to the power 4 with respect to x. Well, we know how to do that. That's just 4 times x cubed. That's power rule. Plus, now you have two things. You have x and you have f of x. So you have to use the product rule. So this is a product of two functions. You have f of x as one function and you have x as the other function. So we take the derivative of x first, which is just 1, and you multiply it by the other thing, so f of x. So we just have f of x plus, Now we leave x how it is, and we take the derivative of f of x. We don't know how to do that, so let's just leave it as f prime of x. That's the derivative of f of x. We're just calling it what it is. It's the derivative of f of x. Plus, how do you take the derivative of f of x squared? Well, we can use the chain rule. So you have 2 times the derivative of f of x times f of x to the power 1. And that is equal to the derivative of 25, which is 0. So that's done. Well, now you have 4x cubed plus, what's f of x? F of x is equal to y, right? So you have 4x cubed plus y plus x times, what's f prime of x? Well, if y is equal to f of x, then dy by dx is equal to f prime of x. Remember, this is just notation. This is all the exact same thing. So you have x times dy by dx. This is in brackets because you're multiplying these together. Plus 2 times, what's f prime of x? Again, that's just dy by dx. Times f of x to the power 1. This is to the power 1. F of x is just y. So you have 2 dy dx times y. And that is equal to 0. Well, what can we do now? To find dy by dx, we can just rearrange this equation. So if you bring dy by dx to the other side, or let's bring these to the other side. So you have minus 4x cubed minus y is equal to x dy by dx, or x times dy by dx, plus 2y times dy by dx. Well, now dy by dx is on the same side, you can just factorize it, right? So you're left with dy by dx times x plus 2y is equal to minus 4x cubed minus y. And now you can just divide both sides by x plus 2y, and you're left with dy by dx is equal to minus 4x cubed minus y divided by x plus 2y. And that is your dy by dx. Of course, it's in terms of x and y, because our original function was in terms of x and y. So it's going to be pretty standard that you get the derivative in terms of x and y as well. But if you have to separate this equation, or even a more difficult equation, well, some of them can't be separated. There is no way you can separate them. But let's say this could be separated, then it would take you a lot of chain rule and being very careful to get the same answer. And this is the correct answer. So let's do another example, but just do it much faster. So let's say we had sine of x times y. This is sine of x and y. It's 2 different functions. Plus yx squared plus xy squared is equal to 3. How do you find the derivative of this function? Well, you want to find dy by dx, so let's put that over here. Is equal to question mark. Well, we start with this. So this is a product of 2 functions. So you take the derivative of the first function multiplied by the second function. So you're left with y times cosine of x plus, you leave the first function how it is, sine of x, times the derivative of the second function, which is just dy by dx, right? Plus, now it's again 2 functions. So what's the derivative of y? That's just dy by dx. So you have x squared dy by dx. Plus, you leave the first function how it is, that's y, and then the derivative with respect to x of x squared is just 2x. And then again, the product rule. So the derivative of x with respect to x is just 1, so you're left with y squared, plus x times the derivative with respect to x of y squared is going to be 2y dy by dx. And this is equal to 0, of course, because derivative with respect to x of 3 is just 0. Well, you can see you have dy by dx over here. You can just factorize it and rearrange the equation. So you're left with dy by dx. And then what do you have here? You have sine of x plus x squared plus 2xy. That's sine of x, x squared, and 2xy. And then on the other side, you have negative y cos x minus 2xy minus y squared. And then to find dy by dx, you can just, let's do it right here. You can just divide both sides by the coefficient of dy by dx, which is equal to minus y times cosine of x minus 2xy minus y squared, all divided by sine of x plus x squared plus 2xy. And that's how you take implicit derivatives. So the easy way to think about it is, imagine if y was just x, right? How would you take the derivative of that? So here you have y squared. Imagine if that was x squared. How would you take the derivative? That would just be 2x, right? So you take the derivative like that, but instead of 2x, you make it 2y. And since it's actually y and not x, you have that dy by dx just staying there, and you just add that at the end. And if it's just in terms of x, then you just take a normal derivative however it is. So derivative of x is just 1, so you just have 1 times y squared over there. So yeah, just think of y as x, take the derivative with respect to x of it, and then just add a dy by dx in front. That's like an easy way to remember it. But the intuition behind it is that you can use this thing right here, y is equal to f of x, and then you realize that actually, if you simplify further, then you do get the exact same thing. So let's do an example question and see what they ask us and see how we can apply this. So the equation of a curve is x cubed plus 3x squared y minus y cubed equals 3. Show that dy by dx is equal to that. Well, that's pretty simple. That's what we've been doing. So find dy by dx on this. So on the left hand side, with respect to x cubed just becomes 3x squared plus, well, these are two functions. This is 3x squared and y. So derivative of 3x squared is 6x. So that's 6x times y plus derivative of y is just dy by dx. So you have 3x squared dy by dx. This is just a product rule. Minus the derivative with respect to x of y cubed is going to be 3y squared times dy by dx. Like as I said, imagine y was x. That would be x cubed. So you take the derivative of that, you would get 3x squared, and then you have a dy by dx in front, and then replace x with a y. So you're left with that. Is equal to the derivative with respect to x of 3, which is just 0. So we don't care about that. Well, now you can just rearrange this equation, right? So you're left with minus 3x squared minus 6xy is equal to, I brought this to the other side, is equal to dy by dx times 3x squared minus 3y squared. You can divide both sides by 3x squared minus 3y squared, so you're left with dy by dx is equal to minus 3x squared minus 6xy divided by 3x squared minus 3y squared. And now we need to factorize because it's not in the form that we wanted, so let's take minus 3 out on both sides. So you're left with dy by dx is equal to minus 3, and you have x squared plus 2xy. And then over here, if you take minus 3 out again, you have minus 3, and then you have y squared minus x squared. I just switched the order of these two around because I want the positive in front. Well, you can cancel out the minus 3's, and you're left with dy by dx is equal to x squared plus 2xy all divided by y squared minus x squared. And is that what we wanted to show in the first place? X squared plus 2xy divided by y squared minus. Yep, that is exactly what we need to show. So we have proven this to be true. So that's done. Let's do the next part. Find the coordinates of the points on the curve where the tangent is parallel to the x-axis. So what does that mean? So the tangent is, as you said, dy by dx gives you the gradient, right? And if it's parallel to the x-axis, what does that mean? That means, so let's say you had this right here. This is the x-axis, and this is the y-axis, as usual, right? If it's parallel to the x-axis, that means it looks like this. The tangent, let's say whatever the curve is, let's say it's like that. Parallel to the x-axis means it looks something like that. The tangent is just a horizontal line. Well, when will you get a horizontal line? When dy by dx is equal to 0, right? So if dy by dx is equal to 0, that's when the tangent is parallel to the x-axis. Because the gradient of this line is 0, so that means, or the slope gradient exact same thing. If it's equal to 0, that means the tangent is going to be parallel to the x-axis. Well, we already know what dy by dx is. It's x squared plus 2xy over y squared minus x squared. So we can write that again. So we have x squared plus 2xy all divided by y squared minus x squared. And that's equal to 0 because this is dy by dx and that's dy by dx and it's equal to 0. Well, multiply both sides by y squared minus x squared, but that doesn't really do anything because it will cancel out. So all you're left with is x squared plus 2xy is equal to 0. What can you do now? Well, you can factorize an x. So you have x plus 2y is equal to 0. So you have either x is equal to 0 or x is equal to negative 2y. That's just solving from this equation right here. Well, let's find the coordinates of the points in the curve where it's parallel to the x-axis. So when x is equal to 0, what is y equal to? Well, we have 0 cubed plus 3 times 0y minus y cubed equals 3. So you have 0, 0, and minus y cubed equals 3. So minus y cubed equals 3. So y cubed is equal to minus 3. And then y is equal to the cube root of minus 3. So we can write that back here. So one of the coordinates is 0 and cube root of minus 3. And the other coordinate is minus 2y. And then, well, let's solve this equation. So x is equal to minus 2y. Well, if you put minus 2y in for x here, you'd get minus 2y cubed is minus 8y cubed plus 3 times minus 2y squared is 3 times 4y squared times y minus y cubed is equal to 3. Well, now this equation is just in terms of y cubed, so we can solve that. So we have minus 8y cubed plus 12y cubed minus y cubed equals 3. Minus 8 plus 12 is positive 4. Minus 1 is positive 3. You can divide by 3 on both sides. So you're left with y cubed is equal to 1. Y is equal to the cube root of 1, which is just equal to positive 1. It has other answers too, but those are complex. We don't worry about them. So we can just write positive 1 as our other solution. And that's it. Those are the 2 points on the curve where the tangent is parallel to the x-axis. So at 0 and the cube root of negative 3, which will be somewhere over here. So there will be a tangent here parallel to the x-axis. And wherever the point 1 is on the y-axis, so wherever, let's say that's 1. And then wherever x is equal to negative 2y. So that's actually equal to negative 2. So negative 2, 1 is the other point. Because we have to have it as numbers. Since x is equal to negative 2y and y is equal to 1, then x is equal to negative 2 times 1. So negative 2 and 1. So here and here is another point where the tangent will be parallel to the x-axis. Let me draw it parallel. So yeah, that's all about implicit differentiation. I hope that makes sense. And yeah, like, comment, share, subscribe, all of that, and let me know what you want to see in future videos. This is going to be a quick video on like a harder example of implicit differentiation. So a curve C has equation cos y is equal to x for x between negative pi and pi. Use implicit differentiation to show that the second derivative of y with respect to x is equal to a negative cotangent of y times dy by dx squared. So how do you do that? So let's start with this equation here. So let's take the first derivative on both sides. So you would have derivative of cosine y is negative sine y times dy by dx. If you don't understand where this came from, you should probably watch the first video on implicit differentiation. And then this is equal to derivative with respect to x of just x, which is just 1. So that's the first derivative, but we don't really care about that. Now we take the second derivative. So let's take derivative with respect to x on this thing again. So the derivative of negative sine y times dy by dx. So treat this as two different functions. So you have negative sine y as one thing and dy by dx as the other. So the derivative of negative sine y is negative cosine y times dy by dx. And then is the product rule, so we just multiply it by the second function, which is dy by dx. Plus, well, you're left with negative sine y, which is the first function, we don't do anything with that. And you multiply it by the derivative with respect to x of dy by dx. Well, what's the derivative of a derivative? That's just the second derivative, right? So you just have the second derivative right here, d squared y by dx squared. And this is equal to the derivative of 1 with respect to x, that's just 0, because the derivative of a constant is just 0. Well, so now you have minus cosine y dy by dx all squared minus sine of y times the second derivative of y with respect to x is equal to 0. Well, now we can just rearrange this equation, right? So you're left with negative sine of y times second derivative of y with respect to x is equal to, you bring it to the other side, you're left with cosine of y times dy by dx all squared. And now you want it in this form right here, second derivative of y with respect to x. Well, you can just divide by negative sine y on both sides. So you're left with the second derivative of y with respect to x is equal to, well, what's cosine divided by negative sine? That's just negative cotangent of y, of course, times dy by dx all squared. And that's exactly what you have to show. You have to show the second derivative of y with respect to x is equal to negative cotangent of y times dy by dx all squared. And yeah, that's a harder example of implicit differentiation. This is from a further maths paper.